right, so next up we have Piotr, and he will be speaking about hypervisors being enabled directly in the firmware. Enjoy.
Hello, everyone. Thank you for coming to my talk. I want to tell you a little bit about our story, how we enabled small Bertrand hypervisor in firmware or added it as a payload to core boot. So my name is Piotr Król. I'm founder and embedded system consultant at 3M It's a Poland-based embedded system consulting company. I'm a huge fan of open source firmware, interested about platform security and trusted computing. So you can reach me on various social media. Feel free to ping me if you have any questions related. So what we will talk about, a little bit of introduction and terminology about the hypervisors. I'm not a hypervisors researcher, so I will not give you a PhD level talk about that. I hope that some basics are already known. I will talk a little bit about the Bertrand, what it is and what it tries to address. And then we will go to hypervisor as a payload in core boot firmware. Little bit demo. Unfortunately, we have to stick to MP4 recording. I forget power supply for my motherboard, but if you will be interested to see that live, I would be glad to show you that this is not any fake and we're not just making some video cheats. And then I will tell you a little bit about the issues and further work that we plan to do. So what was the goal? The goal was to create a firmware that can start multiple applications in isolated virtual environments. Why we did that? We did that mainly to improve our hypervisor flow and to learn more about the hypervisors, since there is market demand for that, and to understand what kind of capabilities various hardware platforms have. Definitely, silicon vendors expand support for virtualization pretty fast. We have VTD, VTC, and probably we will see a lot of more virtualization-related features in future. Okay, so maybe some definition. This is very kind of just to start. So virtualization is the application of the layering principle through enforced modularity, whereby the exposed virtual resources is identical to the underlying physical resource being virtualized. So, so this layering is kind of a single abstraction layer. Example of this virtualization is like we have, for example, memory, which we want to somehow expose higher, and we have unified layering for that. So virtual memory write is kind of way of layering. We're exposing physical resource, which is disk, in a little bit different way, which is write. So we can see either bigger or redundant array of disks, and this is the same concept. And enforced modularity means the person who see the things from top of that layer cannot get through and see what is below. So the virtualization gives us that isolation. So VM is the abstraction of complete compute environment. Hypervisor is a software that manages those VMs. We will speak about the various types of hypervisors later. And virtual machine monitor is a portion of hypervisor which is just responsible for CPU and memory virtualization. So full hypervisor also contains I/O management. Okay, what types of hypervisors we typically have? So type 0 is not official name. It's very unofficial, I would say. We are most frequently play with type 1 and type 2. So type 2 is, for example, VMware, or Oracle VirtualBox, or QEMU. How it works? Simply in operating system, we have some module, or even this is purely software, and we just run hypervisor and can run some various OSs inside. Other model is type 1 hypervisor, where we, and for example, Zen is type 1 hypervisor, or Hyper-V, or VMware ESX. where we just bare metal run the hypervisor, and inside we can run various operating systems. If we're talking about type 0 hypervisor, which we can call 3M Visor, which we develop, and other IBMs or L4, this means that we have firmware inside which we put a hypervisor, and then we just run from that point OS. It is used in embedded environment frequently. Okay, a little bit about the embedded hypervisors or embedded bare metal hypervisors on the market. So it's not so old technology, I would say. It's relatively new to the industry. It started to be used in 2000. It is used in mission and safety critical applications. We saw that in robotics, in automotive, in medical industry. So what it gives us is strong isolation for example, non-critical and critical computation. So let's say we have two virtual machines, one doing some critical computation, which is very important for us so the application perform correctly, and other, if there will be any failure there, we don't care, which we will simply recover from that point. Also, we saw applications where we have fault detection. So one VM doing one calculation, and other VM reverse that computation. And if it sees some difference, it starts to claim that there is some fault and take decision to, let's say, run some security procedure or some recovering procedure. There is also need for running legacy code. So, for example, it may happen that we have some legacy code, but we want to move on with new features, and we cannot simply change that legacy code. So because of that, we just isolate legacy code in some VM, giving it the resources that it needs, and the new features we adding in separate VM. Also, migration from the unicore to multi-core system is simplified thanks to that, because we can scale thanks to virtualization. Manageability is other embedded hypervisor feature, which hypervisor gives us layer for managing those virtual machines, checking its states, maybe updating them, and thanks to that, we have more features on the platform. Also, I saw that cost saving can be a factor because this, thanks to running multiple isolated applications on one SoC, using just simply driving the interfaces to given VM, we can move system which is distributed on various microcontrollers to one system which is on one chip, and this saves cost. So how it looks in firmware? This is what we built. So we have CPFS, typical core boot phases, which is boot block, ROM stage, and RAM stage. And from RAM stage, as a payload, we created 3M Visor or Bareflank payload, which creates a hypervisor. Then this hypervisor can run various VMs. For example, in one VM, we may have CBIOS. In other, we have like arbitrary payload. It can be some RTOS, or we can also use grab or Kayama core to boot operating system. Okay, what is Bareflank? So Bareflank is a lightweight hypervisor written in C++. It is managed by Azure Information Security. It supports Windows, Linux, and UEFI, and from now also coreboot. It supports mostly Intel, but the structure of the code is prepared to support ARM and AMD, and that support is planned in the future. And most important features of that, it provides memory management support, it has serial support, libc++, also vCPU management, and VMX logic management. So typically, how you use Bareflank is a kind of framework where you scaffold your own hypervisors, and then you develop correct VM exit handlers to support various operations. And Bareflank was created for interception and kind of security research needs, I believe. And because of that, it's a little bit different use case than we applied it, but that's caused some future assumptions, I would say, or design assumptions. Okay, so what we really built. There is VMM code delivered as C header. It is generated by Berfrank SDK, you can say. The bytecode we put bytecode into this VMMH. It's 88,000 lines of code, but it doesn't matter. It's just bytecode. It's 1.2 meg without any customization. So it's like out of the box, we're getting 1.2 meg. We created Berfrank driver, which is minimal C code, which helps us hook everything to launch virtual machines, and it contains like it fully contains around 6,000 lines of code. It required lib payload modifications because lib payload, which is required to build a payload, was just 32 bits, and we had to extend it to support 64 bits. And other headers we had to import from Berfrank projects because we use functions from there. So the tree looks like you see here. It's inside coreboot projects. It's on our GitHub. You can use that, compile and test. Okay. So typically, Berfrank uses OS API. If you use it as a type 2, because Berfrank can be used as a various types of hypervisors. If you use it as a type 2, it uses OS specific API. If you use it as type 1, it uses, for example, UEFI boot services. But of course, when we're using coreboot without UEFI payload, we don't have UEFI boot services, so we have to extend lib payload to add some support. So we added support for 64-bit. We added 64-bit exception handling. And of course, we didn't care too much about the device drivers. This may still require some fixes. So we had some size problems because we just have to, if we boot some VM, we just have to have something inside SPI. We don't want to use disk for loading additional bootloaders or anything else. So we want to have everything in SPI. And of course, we need some additional stuff like CBIOS. The hypervisor have to be there. Also, we need coreboot there. So it happens and we have just 8 megs. So we had to compress some stuff to enable that. Okay, what other problems we have? One of the problems was that coreboot tables are not modified by lib payload. So coreboot tables describe memory map, and then this memory map is reused by, for example, by CBIOS. So then we run payload, which is our Berfrank hypervisor, and then lib payload just allocates some memory, for example, for VMM. And if then CBIOS, and of course, lib payload do not modify coreboot tables to indicate that that memory was allocated. And then when we jump to virtual machine and try to use CBIOS, which of course use coreboot tables, then we can have problem because that memory can be already corrupted. So how we fixed that? First of all, at the coreboot level during the build, we reserve some memory for VMM, and this memory is just reserved over whole time. And then yeah, that was the main fix. So the compilation time, it should be solved by a runtime solution, but we didn't have enough time to apply that. Other problem that we faced was that VMX extensions have to be run on all cores, because if we have situation if one of the core does not run VMM, then some software which is there can corrupt the memory, and we faced the situation. We didn't know what exactly going on, and after some time realized that at some core, at 4 core, we didn't run the extension, and because of that, we corrupt memory of other VMs or even VMM. So so we had to implement in lib payload MP code that gives ability to say, okay, run VMX on this core, on that core, and on other core, and remember to run on all cores. Okay. So I mostly told you about that, but there is other solution for this problem with core boot tables. Of course, we can use EPT, but the problem is that, of course, Berflank contains some support for that, but the problem is that there was also a lot of things that you had to additionally implement to manage EPT correctly. And of course, this would have a significant impact on hypervisor size, and we cannot approach that because we have limited the SPI size. We have just this 8 meg, and we just couldn't add that. Yeah, and it can be now suitable for embedded hypervisors because of the space limitation and probably performance. So how the payload look like and what is designed, what the components it has. So as I said, we're starting with core boot, and we have Berflank payload. Inside we have this Berflank driver, BF driver, and BF driver contain lib payload, which provides us support for entry point, for the 64-bit, for some memory management. Of course, we need CBFS functions to read CBFS and get any bootloader from there if we want to run VMs. And yeah, and of course there is payload loader there. And there is this logic like we first load VMM, so we load on the cores that we want to run VM. Then we start it and we start payloads inside given VMs. The other problem that we had to solve here is this switching from 32 bits to 64-bit, and then if needed by payload switching back to 32 bits. For example, CBIOS is 32 bits, so we have to switch back. And this kind of game had to be implemented. Okay, so maybe I will try to describe what's going on with the demo. Okay. So what you see here on the top left, you have serial console of the platform of the Minnow board that we used for development, and you will see that we will boot Berflank. It will boot Berflank as a payload from core boot, so we boot in core boot. So it's I know that it's very hard to see, but believe me that there will be Berflank here, and yeah, and Berflank right now starting VMs, like 4 VMs, one on each core, and on one VM we see it starts core info payload. So this is just basic payload of core boot, which just show processor and its features. You can also see that we have some memory reserved. This is a memory reserved for VMM. Yeah. So on the other core, we start Linux kernel, which we want to show that after booting this Linux kernel, we can, on the same machine, have access to Linux, which is, of course, we don't have serial output. We also didn't manage to enable any video output, but we run some service which will show that this VM really works with Linux inside. Okay. Yeah, we can have various payloads use it. Yeah, we put the Linux kernel in SPI Flash as well as in InterMFS, so this machine does not require any additional storage. It's directly from SPI Flash. Yeah, there is not a lot of the space, but still something. So yeah, so also this, of course, on this one core with limited memory, this Linux boots quite long. Like it takes like 40 seconds, but this shows that exactly on that machine we have running Linux, and we can telnet to it, we can SSH to it, and we can even we can even run other stuff. So we just build those two VMs, one with core info payload and other with Linux kernel. And I believe on this video we have also some inception. Yeah, so you can see that there was my presentation was also run inside this Linux. Okay, anyway, let me close that. Okay, this is description of the memory layout that we used. So on top you see VM1, how VM1 see the memory. So it's see core boot tables, some reserved memory which is for VMM. It see other area of reserved memory which is really a copy of the of the core boot tables to present that to the second VM. And fourth region is ACPI, PCI, and all that stuff. Of course, there is no sophisticated device management and exposing those devices to VMs. So if those devices together will try to talk with hardware, probably everything will crash. But anyway, it is possible to implement that in hypervisor. And second VM, which is our Linux, sees the memory a little bit different, and this is this third line. It's just see that the beginning is this this copy of the original area. So yeah, and things that this. So also it is in the same place. In the same place, you see VMM reserved memory. So this is mainly like that. So what we would like to do with that in future. So first of all, the problem is that Berflank is built completely as a separate project, and you have to deliver components of that project or artifacts of that building to the core boot, and then do it manually. We would like to integrate Berflank building into core boot. So some configuration. Right now we have almost no configuration. Everything is hard-coded. So if you want two VMs in that configuration, you just have to manually hard-code that. So of course, this needs some customization. Someone would like to have 3 VMs or 4 VMs with various other payloads or for various other applications. Then of course the configuration have to be extended. We should improve definitely memory mapping. So maybe use of this EPT, like flexible use of EPT and leveraging all the features of the platform would be needed. Of course, the problem is also that Berflank is very fast-moving target, and sometimes there are big code drops, like 60,000 lines of code, and you're just losing your ground. And because of that, like we frozen our code base in early 2019. It changed significantly from that time, and we would like to rebase on the most recent version. And of course, it would be great to provide support for AMD platforms, like AMD getting a lot of traction recently, and we're also supporting AMD on other hardware. So it would be great to enable Berflank there. Okay, that's mostly it. I get through that very fast. So I thought that I will get through hardware demo. It should take more time, but this is it.
So is this a Berflank based on existing code base, or is this completely from scratch?
So Berflank is a scaffolding, we can say scaffolding framework for building hypervisors, and this is like clean build of like plus our minor modifications, but everything is public.
So it's not based on KVNGen or Acorn or any of these.
No. This is like Bearflank is completely other hypervisor. It's like SDK for building hypervisors. You can
building.
say. Yeah.
Oh, okay. So in this case, if we have application like one VM, one partition, is it also suitable for that purpose?
Yeah, I believe like Bearflank is good for embedded environments. It's not like for general purpose hypervisor environment.
Thanks.
So I've been having discussions with some people at Intel about, and with Patrick Georgie in the past, about maybe a more componentized RAM stage that would be loaded as a payload, not a stage.
Mm-hmm.
Would that be of any help in the kind of thing you're talking about, or is it really not any connection? I was just wondering if we have more componentized RAM stage, maybe we could build your Bearflank stuff in more easily than we do as just a separate payload.
Yeah, definitely. Like, yeah, that would help because we already had idea to integrate that into core boot, and I was like, this was internal discussion in 3MDev, and we argue rather that this would not be approved by core boot community because, like, like how it would be, and so there was idea it would be easier probably because we don't have lib payload and all this game with lib payload, and I know there is also idea to have core boot in 64 bits. Yeah. So if that will also be implemented, then we will have like 2 wins at least.
How difficult do you think it will be to reproduce something like what you've done on hypervisors that are a little bit more complex, like let's say Acorn or Zen?
We try it, Acorn. Like we give it a try, and Acorn is bloated, to be honest. Like, and there is Service OS, and like our idea was to start from SPI. So like Acorn for sure, no. Zen is huge for x86. On ARM is much smaller. Maybe would be possible to reproduce.
Okay.
So I know other thing, like maybe we didn't explore all the possible paths for embedded hypervisor. For example, recently I know that there is a work in L4RE project. So those guys probably, if someone from that environment, probably can argue that this would be maybe better solution because more components are ready.
Do you know if Bearflank will ever support IOMMU to actually separate the hardware from different VMs?
Like natively, I don't know. Like you always can add that, but it's kind of additional work. I don't think like they have idea of doing that natively. So because I assume there would be need for driver and some way of configuring, okay, I want this separation. The question is how it will play with various hardware configurations.
Yeah, we implemented VTD support in EFI like 2 years ago at Apple, and it was really difficult, but when it works, it does work. So it works on almost all Intel systems we have now. And the biggest difficulty was actually get the right people from Intel to tell us how to debug out of things that have like not this. There is no documentation for this corner and nobody knows.
Yeah.
So for an open source, I'm looking forward for somebody to redo the work and then publish the license for it to be used as a knowledge source, because now I would like to have it somewhere and can't deliver.
So, it would be great if you contribute to that to open source, but I believe this is huge value for company. I did stuff for AMD. Like last year, I have a talk about AMD IOMMU and enabling on PC Engine's platform. And yeah, I know the pain. Like I understand that. And still, it is buggy. There we have some facing some corner cases where people complaining devices not work correctly when it's enabled by default.
So Could you dynamically adjust the memory allocation? For example, if one VM needs a large memory, another VM needs a less memory. So could you, dynamically adjust the memory for each VM?
Yeah, like not dynamically, like not in a way, not runtime. Like we're doing that, it's hard coded. Like this is
to reserve the memory for each VM in the beginning and then
Yes.
change after that.
yes, like you cannot change runtime, at least in current implementation.
So that means that in the beginning you have to know the requirement for each VM about the memory.
Yes, that's
use.
normal requirement for embedded and embedded environment. So in embedded hypervisor usage, typically you know what VMs you want, how many of them, what resources they need, what devices they need, and this is like predefined environment.
Okay.
I have a few questions, and I apologize if I missed it, if it was already in your presentation. The first was, I don't believe that you talked about why you chose Bearflank.
Because we analyzed Bearflank versus Acorn and decided that Bearflank fits our ability to customize to our needs, and it's small enough. We can build hypervisor small enough to fit in SPI.
Okay, thanks. The other question I had was, you talked about other pieces that you were carrying, I guess some patches to Corbett and things like that. Or were you putting that in your own builds?
Yeah, we would be glad. Like Bearflank building environment is CMake based, and like I don't know like how it will fit into the environment. It also depends on demand. If there will be demand, like we are more willing to provide that. Right now, it is integrated on our core boot fork. It's open. It's like we don't hide anything. So, but I don't know when it may happen and in what form. Like because it depends on core boot community decision.
Okay. So then, are you carrying your 64-bit trampoline stub in your Bearflank port as well?
Like lib payload, I believe lib payload will be contributed. I don't know if we sent patches already. Lib payload will be contributed because there was a work about 64-bit lib payload, and I believe more people can contribute from that. Bearflank, I don't know how many people really can contribute from that work. That's why I'm giving this talk and to get some feedback if this is really interesting, if this makes sense. But I see quite a lot of you, and I believe it makes sense.
Thanks.
I missed the beginning of the presentation, so I don't know what is the size of Bearflank compared like to Zen, for example.
I don't know if we can compare, and if we should, this is completely different. So 1.2 meg VMM and 6,000 lines of code of the driver. You can say like the heart of the payload. Which 1,000 line of code is lib payload modification to support 64-bit, and 800 lines are just copied from Bearflank because we need headers.
Okay, because I'm a contributor for the EDS project, and before we needed to have Zen inside the SPI flash because of constraint, and with key exec being modified and everything, we don't need to do that. But like Zen was in.
Were you able to succeed with that?
Yeah, but Trammell did it, like Trammell Hudson. Like it was working. So if you want to check, because like if you want something that is embedded and really small and predefined already, like your machines that you want and everything, like Zen seems to be able to be reduced.
So how big was Zen in that situation?
It's still pretty big though.
Yeah, I thought it was like 1 meg or something. I don't know the size constraints of all of this, but I was questioning.
It comes, I think, that's why I was asking. I think it comes with the same set of constraints of like setting up the system just right with the service VM and stuff like that. So
yeah, so Zen will require DOM zeros, and DOM zero is fully featured operating system, and we don't really need that.
Well, speaking of ARM, I mean, there's actually DOM0 less than now, so like it's all evolving pretty quickly. But that work that he has done, it's still pretty big from what I understand. For the purposes of this presentation.
Yeah, Zen was like too big for us in that case. I know that there are some hypervisors coming, which will kind of fulfill those requirements, but they were not available at the point we developed that.
We still have 10 more minutes, so take the chance.
Yeah, anyone have like a Mino board power supply or something like that? I just missed my one, and because of that I cannot show live demo. I would just prove that this is real thing and we can switch. This is quite cool that on one side we have, on serial for example, we have payload. It's arbitrary payload of core boot, and on the other side we have fully featured system. Yeah, so we were also surprised that Linux boot without, to be honest, much work using Bearflank.
We're gonna try and get you one.
Okay.
Not within the next 10 minutes.
Yeah, sure. Like, sure. But also, if anyone would be interested in seeing that, presented on hardware, I would be glad to show that. Okay. Any questions? Yeah.
All right, then thanks again.
Thank you very much.